We have come to the last lecture of this module on advanced method for the solution of Ax equal to b. We have seen in this second part of this module methods like successive over relaxation, alternating direction implicit method, and the strongly implicit procedures, all of which are attempts at trying to accelerate the rate of convergence of an iterative scheme. Multigrid methods are probably the best at making this acceleration. These have been in development since mid 70s and 80s, and now these have reached a stage of fruition that these are now routinely being used for the for CFD type of problems. So, we would like to see what is the principle behind this and how it actually works, but in an academic context, in the sense we will take the simplest possible example and we will try to understand how this whole thing works. The idea of this multigrid methods is that in an iterative method we are trying to reduce the residual, and residual represents the degree of non-satisfaction of the current solution with respect to the of the original governing equation Ax equal to b, and this satisfaction is non-satisfaction is there because there is some error in the solution. So, we are trying to reduce the error. Now, this error is usually can be decomposed into many components, and some methods like the Gauss-Seidel method are good at reducing error which is at the smallest scale of error, and there are some other methods which are not so very effective at that. So, if you are if you are using Gauss-Seidel method, then the error, that part of the error which is there in the smallest wavelength gets reduced very fast, very efficiently, but the larger wavelength errors are not damped so easily. You will have to work on it many times before you can damp it. An illustration of that is what we are going to see to begin with. So, we are saying that multigrid methods rely on the idea that some iterative methods such as the Gauss-Seidel method and also the strong implicit procedure are good at damping out errors associated with high frequencies or short wavelengths, but are not effective against low frequency or long wavelength errors. The distinction of short and long wavelengths is with reference to the grid spacing. So, if you have an error which varies as twice the wavelength of twice the grid spacing, that is the shortest possible error, and so that is considered as a short wavelength, and long wavelength errors are anything of the order of 5 to 10 times the grid spacing. So, we illustrate this error damping properties of the Gauss-Seidel method by considering the example of a 1D steady state heat conduction in a rod, so that you are expecting a linear variation, and this is the kind of linear variation that we are looking at. We have x going from 0 to 1 and t going from 0 to 1 as you go from x equal to 0 to x equal to 1. So, it is a straight simple problem, 1D steady state heat conduction with constant thermal conductivity. So, alpha d square t by dx square equal to 0. So, that is the kind of thing without any source term. So, that will lead to a truly linear variation like this. Now, what we are doing here is that we are imposing on this true linear variation, we are introducing some error which is spatially distributed in the form of wavelengths, okay, in the form of sinusoidal wave components, and what you see very faintly here and we will see later is the error which is superposed on this linear variation. That is why you have this waviness that comes here, and this waviness is composed of 3-4 different wavelengths, okay, one which is short wavelength, one which is bigger, and one which is even bigger. So, a Gauss-Seidel method or any other method would try to damp out these errors so as to give rise to the linear variation. So, once you have, so right now this is the kind of variation, this is the kind of expected t that we have, and we would like to go from the blue one, okay, the faint blue one to the blue one to the red one, and that is happening over 50 iterations in this particular case. So, we are considering a 1D steady state heat conduction with a linear variation, and on top of this linear variation we are adding certain error of different wavelengths. So, we are saying that T at any point is that given by the linear variation between 0 and 1. For example, at midpoint x equal to 0.5, we expect T to be 0.5, but now we are saying that T is 0.5 plus some a sin lambda x plus b sin okay, a sin x by lambda 1 plus b times sin x by lambda 2, like that. So, that is a variation that is being imposed on this, and we would like to see that if you take this wavy T as your initial guess, then after how many iterations the waviness disappears and we get a perfectly linear variation. That is what we are trying to see here. It is difficult to see in this, so we have a magnified version here. The one that we can see here is the initial solution. You can see it is going up like this and then going up, going down and then going up big way, coming down here and then like this. So, this has a variation of this wavelength plus a variation of this wavelength. So, there are two variations, one of what is eventually this variation, the red variation, and one which is of 1/4 of that variation wavelength here. So, the combination of these two is giving rise to these small wavelength variations plus large wavelength variation. So, this is what we have as the initial guess. Now, if you then put the Gauss-Seidel method for the solution of these equations, this is with a delta x of 0.001. So, between this and this we have 100 grid points and 100 individual values, and so between this and this we have it should be delta x of 0.01. So, it is not 10, it is 0.001 I think. So, it should be large number of grid points here, so as to give you this. So, if you start with this, then after 5 iterations it becomes like this, a very faint grey line, and after 10 iterations you see the blue line, which is this one here, and after 50 iterations you see the red line. Now, what is there in red line and what is not there in red line is of significance. The red line here after 50 iterations has still retained the long wavelength variation, okay, but it does not have the short wavelength variation that is exhibited in the initial guess. So, short wavelength variation is going up and coming down over this small interval, again it is going up and coming down over this small. So, over a short variation, small interval, x interval, it is already showing a sinusoidal variation, but this one is not showing any sinusoidal variation of that wavelength, because it is all a single sinusoidal variation corresponding to a wavelength of from here to here. This is the wavelength that is remaining after 50 iterations, whereas in the initial variation you have this long wave variation plus a short wave variation corresponding to this. So, the short wave variation got damped within about 10 iterations, but the long wave is persisting after 50 and after 100 and even after 200. The amplitude is decreasing, but even that variation is still there. So, it has taken 200 iterations or more to bring it almost up to the linear variation, but out of this the variation corresponding to the short wavelength is damped out within 10 iterations. Okay. So, now therefore, if you have an error which is composed of very short wavelength variation and a longer wavelength variation, you will have to do many computations, many iterations before you can reduce the long wavelength thing, and that is what will hold up your solution. because your solution requires you to have very small residual, and a variation like the red one here will have a fairly large residual, and that residual will have to go down, and that will happen only as this approaches this linear variation, and that has taken 50 iterations to come up to this, and then 100 iterations to come up to this, and 200 iterations to come up to this. Now, if we did not have this delta x of 0.01 or 0.002, I think, instead of that, if you had 4 times the grid spacing, then this same blue variation is shown in the this red variation is shown here. Okay, but you can see that this is like a piecewise linear, so you have one grid point here, one grid point here, one grid point here, like this. So the delta x here is bigger, 4 times as big as this. And if you start with this variation as the initial guess, after 10 iterations you have come up to this. So what has taken you 200 iterations to or 100 iterations to come up to this variation, you have achieved that in 10 iterations on a larger grid, because on this large grid this variation is like a short wavelength variation. So the same Gauss-Seidel method with a delta x spacing of 0.01 or 0.002 here is taking 100 iterations to reduce this wavelength error in the red thing, but it is taking only 10 iterations on a grid spacing which is 4 times bigger. So that means that a scheme like Gauss-Seidel can reduce the error associated with short wavelengths very efficiently, and at the same time it is very inefficient in dealing with large wavelength errors. Okay. And what are these wavelength errors? We have seen in when we are looking at stability analysis, a Fourier decomposition of an error into number of wave components. So if you have an error in the general case, it can be decomposed into a large number of Fourier components, each of different wavelengths in the x direction, in the space direction. Okay. So in a linear problem, each of those errors needs to be damped out. Each of those red variation, wavelength variation should be damped out so as to give rise to this linear variation. Okay. So what is the damping rate? The damping rate for a given scheme depends on what type of scheme it is, and also on the grid spacing. What is the wavelength of the error wavelength, and what is the delta x that you have. So if your delta x is very small compared to the wavelength, then it will take large number of iterations. If your delta x is small compared to this, then it will take only a few iterations to get down to this. So what do? We cannot choose a wavelength error, because that is imposed by the problem and initial guess and how the error changes. And in the general case, you have wavelengths of all wavelengths, short wavelengths, long wavelengths, even longer variations, long wavelength variations, all of them are there. So if you have only one grid, then you can only damp out wavelengths of the shortest wavelength very fast. So in multigrid, the idea is that you do not have a single grid to deal with to get the solution. You use a short wavelength fine grid to remove quickly the short wavelength variation, and then you go on to a coarse grid, and then you remove again the short wavelength errors on the coarse grid fast. Okay. These things were difficult to remove on the fine grid, because for a fine grid these are long wavelength variation, and that is illustrated here. The same the red variation here is a long wavelength variation for a delta x spacing of 0.01, and it is a short wavelength variation for a delta x spacing of 0.04. That is why it has taken 50 iterations to come from this amplitude to this amplitude. It has taken another 150 iterations to come from this amplitude to this amplitude. But on this, when on a coarse grid where it is like a short wavelength, it has taken from here to here, it has taken only 10 iterations. And so that is the advantage, that is the efficacy of the Gauss-Seidel method in reducing short wavelength errors, and that is also the inefficiency, weakness of the Gauss-Seidel method in dealing with long wavelength errors. So, one possibility is to have horses for courses policy. For long wavelength use coarse grid, for short wavelength errors use fine grid. But it is not easy, because you can have one grid, okay, that is a conventional thing. In multi-grid method you flip, you go from fine grid to coarse grid, but if you ultimately get a solution in coarse grid, then we have too much of truncation error, because truncation error is usually proportional to delta x. We need to solve it on the finest grid that is possible, and there your method is effective only in reducing the short wavelengths quickly, and long wavelengths will take a huge number of iterations. So, in multi-grid method we start with the computation on the fine grid, we do a few number of iterations, maybe 5-10 iterations, and then we take the error from the fine grid to a coarse grid, and there we work some more iterations, and because it is now coarser grid, what were earlier long wavelength, some of them would be damped out quickly, and then we go to the next even coarser grid. So, what the middle coarse grid is unable to damp out quickly, this will be damped out in the even coarse grid, and then you go to the next coarse level. So, the error will also be damped out. So, in each grid you are doing only 10 iterations, and then you go to the coarsest grid, and then you now have reduced error. Use this reduced error to improve the solution on the fine grid, and then you do some more calculations. So, finally you are going from the fine grid to the coarse grid, and then you are coming back to the fine grid, and each time you are trying to reduce error, and eventually when the error on the fine grid becomes very small, at that point you have you can say that you have got a converged solution. But always you are reducing most of the error in the coarse grids and not in the fine grid. So, fine grid is for final tune up. So, this is the idea of the multi-grid, and we will see how it actually gets implemented. So, let us just try to paraphrase this. The key to reducing error quickly is to use a grid in which error is of short wavelength type. However, except in simulated cases like what we have just now seen, typically errors of all wavelengths will be present in the initial stages of an iterative solution, and also for accuracy we would like to have a fine grid, and on this we can reduce only short wavelength errors. So, in the multi-grid technique the equation is solved on multiple grids, grids of different grid spacing. Consider 1D steady state heat conduction equation with just two grids, one fine grid and a coarse grid. You start with a small number of iterations on the fine grid, remove small wavelength errors, transfer a smoother error onto the coarse grid. After some iterations on the coarse grid, you have reduced the large wavelength error somewhat, and then you have now a different error distribution than what you had at the end of fine grid solution. So, from this error you estimate what would be the true solution, and then you give this estimated solution back to the fine grid, okay, and so you get you feed an estimated solution with less error back to the fine grid for further iterations. And in the estimation process you have also introduced some small wavelength errors, you damp them out, and then you reduce the error, and then you bring it back to the coarse grid. So, you continue this process frequently switching between the two grids until the solution is sufficiently converged on the fine grid. So, when you do this kind of computation, we still at this stage do not fully understand this, okay, we will do that shortly, but this is the idea, that you have different grids for the same domain, different grids of different delta x, and you do part of the computations on the fine grid, and then you go to the coarse grid, and then you go to the next coarse grid, and then you come back to the fine grid, and then you keep on doing this and reducing part of the error in the fine grid, part of the error in the coarse grid, and part of the error in even coarse grid. So, by doing this you gain 3 advantages. You get faster error reduction because each error is being reduced efficiently on grid of different sizes, and we know that the grid size does matter when we look at finite difference, when we look at reducing error using something like Gauss-Seidel method. Okay. Faster propagation of information from boundary condition. When we look at a typical elliptic equation, the interior points need to know what the boundary condition is. Okay. So, that information propagates one step, one delta x at a time. So, if you have small delta x, then it takes a large number of steps before the interior point gets to know what is a boundary point. If you have a coarse grid, that boundary point information gets propagated into the interior faster in fewer number of iterations. And finally, we know that the number of arithmetic operations which are required for the solution of Ax equal to b varies as n square, where n is the number of grid points. If you have coarse grid, the number of grid points is less. Okay. So, that means that the solution will take fewer number of mathematical operations. So, the number of mathematical operations that are required on the coarse grid in order to get a solution for the error is far less than what is required for a solution on the fine grid. And so, since you are doing part of the computations on the coarse grid, your overall number of mathematical operations, arithmetic operations is reduced. So, because of all the 3 advantages, you can get much faster solution on the multigrid. Okay. This multigrid can be extended to multiple grid sizes, not just 2, and the more the number of grids that you have, the faster, the better will be the benefits. So, let us just see how it works for a 1D problem. We are considering now 1D steady state heat conduction equation with d square t by dx square equal to f of x. So, with the boundary condition that t at x equal to 0 is t naught and t at x equal to L is T L. These two are specified, T naught and T L are specified, so that you have an elliptic problem, and you have a domain, 1D domain. So, it is going, this is the x direction, increasing x direction, and you have 2 grids in this case, small I and small I minus 1, small I plus 1. These are all the grid points on the fine grid, and capital I minus 1, capital I minus 2, I plus 1 are the grids in the coarse grid, and so you can have a delta, capital delta x, which is the grid spacing, coarse grid spacing, which is twice the grid spacing on the fine grid. Okay. So, we are looking at 2 grids, fine grid and a coarse grid here. So, for point I, which is there in the fine grid and also in the coarse grid, okay, this equation can be written as T I minus 1 minus 2 T I plus T I plus 1 by delta x square equal to F I. This is our conventional finite difference formula at point I with a grid corresponding to the small i's. So, you have I, small I minus 1, this value, small I plus 1, this value and this value. So, that gives you a central difference approximation for this, and if you do this for all the grid points, you get AT equal to B, and then you can solve it. But you are solving the AT equal to B in an iterative way, and we have seen the Gauss-Seidel method. So, after k iterations on the fine grid, the Tk, that is the solution for Tik, satisfies the governing equation with the residual. Okay. So, that residual is such that it is equal to Ti minus 1 k minus 2 Tik plus Ti plus 1 k divided by delta x square is equal to Fi. It is not exactly equal to Fi, but Fi minus rho Ik. Okay. So, this is the residual, and this is the amount which is if this is equal to 0, then you have an exact solution, but if it is not equal to 0, then you have this. So, if you say that Ti hat is the exact solution, then you can say that error epsilon ik is the exact solution minus Tik, and then the error evolves as epsilon I minus 1 k minus 2 epsilon ik plus epsilon I plus 1 k divided by delta x square, and that is equal to rho ik. Now, we can solve this. Okay, this has already been solved for k iterations on this, and in the process all the short wavelength contribution of this error has been already damped out, because the Gauss-Seidel method is very effective in removing short wavelength errors, and so if the error distribution, the spatial distribution has a combination of short wavelength and long wavelength of different wavelengths, then the short wavelength contribution is already removed, and so this has only the long wavelength things. So, instead of solving it on the fine grid, which is small I minus 1, small I plus small I plus 1, we can solve it on the coarse grid. Okay. So, since error is already smoothened, it can be solved on a coarse grid. The error equation therefore needs to be extrapolated or prolongated to the coarse grid. Okay. As it is, this error equation is expressed in terms of small i's with a grid spacing of small delta x. Okay. But so this is not posed for the coarse grid. If we can extend it, extrapolate it in such a way that we have epsilon capital I, epsilon capital I minus 1, epsilon capital I plus 1, that will be like solving the error equation on the coarse grid. Okay. So, how do we use this error, how do we extrapolate this onto the coarse grid, and that process of extrapolation is known as prolongation in the multigrid literature. So, we derive the coarse grid error at error equation at for capital I here, which happens to be the same I here, by saying that this total delta x is composed of this small delta x at I plus half of the error equation at I minus 1 plus half of the error equation at I plus 1. So, this total error here is composed of the error here plus half of the error here and half of error here. Okay. So, we can say that this whole thing is equal to half of the error equation written at I minus 1. So, that is error at I minus 2 k, I minus 1 2 I minus 1 plus epsilon I here. So, that represents the error equation at I minus 1, and error equation at small I is epsilon I minus 1 2 epsilon I plus epsilon I plus 1, and the error equation at this point small I plus 1 is epsilon I plus 1 and epsilon I plus 2. Okay. So, all of this is equal to rho I minus 1, because this is rho I minus 1 k and this is rho I k plus this is rho I plus 1 k. So, this is the thing. Now, when you look at this at the end of k iterations, we do not have these epsilons, but what we definitely have are rho I minus 1 and rho I plus 1. So, these are known. So, the right hand side is known, and we can say that the sum of all these things is now the residual at capital I at the end of small k number of iterations, and so this is the residual at on the coarse grid, and you can now write all these things as on the coarse grid as epsilon capital I minus 1 k and 2 epsilon I capital I k and epsilon I plus 1 capital I k plus 1. So, now if you look at this, you have error expressed at coarse grid points capital I minus 1 capital I plus 1 with a corresponding residual, and for this can be written for all the points. So, this will give us coefficient matrix A times error on the coarse grid equal to the residual. So, this equation can be solved because right hand side is known and right hand side is derived from the residual, which is computed by solving the this equation for each of these for k number of iterations. Okay. So, with the known right hand thing we solve for error at each of these points, okay, on the coarse grid. So, now we solve for capital K number of iterations this coarse grid error equation with residual extrapolated or prolongated from the fine grid. So, we solve this for k iterations and then we get error, and then we say now the true value is the value at the end of small k number of iterations plus the estimated error at this particular point. Okay. So, if you go back to our definition here, we are saying that error is the true solution minus this one here. So, the true solution is this plus the error. So, we had this solution and we have now a revised estimate of error. So, that is so we have the estimated new solution after small k number of iterations on the fine grid and capital K number of iterations on the coarse grid is the value at the at the coarse grid that we had here plus the error here. Okay. So, with this we can say now we can go to the fine grid. We now have an improved solution here and we can go to the fine grid, but the problem is that these estimated values are now available only at the coarse grid points, that is capital I minus 1, capital I minus 2, like this. Whereas, if we want to solve this on the fine grid, we need to know at this point and also on small I minus 1, small I minus 2, small I minus 3. So, for this simple grid we can say that T small I minus 2 is equal to T at capital I minus 1, which is obtained here, okay, and this value is also known. And for the intermediate points we evaluate, we take interpolate from here. So, that is T small I minus 1 is equal to half of T capital I plus T capital I minus 1 by 2, okay. And similarly T small I plus 1 at this point is the average of these two values. So, in that way you can get the interpolated value and the computed value here, the estimated value here. So, by doing this interpolation you now have estimated better solution, okay, better solution of T. Why we say it is better solution? Because you have run some more number of iterations, capital number of k iterations, and reduce the error by solving this residual equation here, and therefore it has less error and therefore it is a better approximation. Now, with this small Ti k plus k as the initial guess, you solve this equation here for another small k number of iterations, and that will reduce the error further, and at the end of that you again calculate residual and then prolongate these things to the coarse grid, and then you come back to the grid and then you reduce the error further. So, that is how you go forward. Okay. So, you solve the original equation in terms of the true variable, in this case temperature, on the fine grid, and after doing certain number of iterations you estimate the residual and then you solve the error evolution equation on the coarse grid. Okay. So, once you get the error estimate on the coarse grid, then you estimate the solution on the fine grid, and then with this improved solution you do furthermore error reduction, and then after that you come back here. So, you switch between the fine grid and the coarse grid, and after that you come fine grid and coarse grid. You solve the original equation involving the true variable T on the fine grid, and then you estimate the error, and then you solve the error equation with the prolongated residual on the coarse grid, and from the coarse grid you have the estimated error. Based on this you estimate the error at each of these points here, and then you can get an improved estimate of the solution after having done some more iteration of the coarse grid, and then you come back to the fine grid. then you can repeat this process, and if you do that over a number of such things, you get an error reduction which is faster than if you were to use only a single grid. Okay. So, that is the idea of the multi-grid method. It can readily be extended to 3 dimensions, and it can be used for not just the diffusion kind of problems, it can be used for other type of problems also. But its best effectiveness is in terms of the diffusion type problems. It can also be extended to unstructured problems, it can be extended to nonlinear problems, but each time you go for these more complications, lot more issues need to be solved, lot more issues need to be addressed, and if you go through the literature you will see some suggested solutions for each of these, and the state of the art is that you can do these multi-grid solutions for real world fluid flow problems. And when you do that, studies show that the number of arithmetic operations for the multi-grid method varies as n raised to power 1.1, where n is the number of grid points. Okay. So, this needs to be compared with n cube number of operations for a Gaussian elimination, n square number of operations for a Gauss-Seidel method, n to the power 1.5 for the optimal SR method, and there are other methods like conjugate gradient method which have as a theoretical limit n to the power 1.25 for the conjugate gradient thing, and here you have n to the power 1.1. So, this represents a significant improvement over the Gauss-Seidel method and Gaussian elimination method, and essentially we are making use of the same Gauss-Seidel method, but we are doing it on different grids. So, there is obviously more overhead, more amount of computation, more difficulty in writing programs and all that is there, but once you overcome those you can get much faster rate of error reduction and much faster turnout of the solution, because it takes only n to the power 1.1. So, that means that it will also easily scale up to larger problems, and so this is often used to advantage when you are dealing with large scale problems involving huge number of grid points. Okay. So, there are problems when you do nonlinear problems and those type of things, those are to be expected anyway, but we can expect some significant improvement over the simple Gauss-Seidel method. So, with this we can close this module, and we can close this module which is specially on how to solve Ax equal to b, and we have seen that there is a vast plethora of models and methods, and these methods can be like direct methods or iterative methods. These can be very basic methods that have been known at the turn of the century or in early 1900s, and but over the 20th century there have been steady improvement in this rate of convergence by doing bringing in vast number of methods that are known to mathematicians, that have been developed by mathematicians, and these are now commonplace in terms of their occurrence in CFD literature, and so these are the kind of methods that are that make CFD what it is today, where you can solve 1,000,000 grid points on your desktop overnight and get a solution. So, something like this would not be possible if these methods were not there. Okay. So, we have finished 5 modules, and we can say that we now have a bird's eye view of the entire process of the CFD, right from formulating the problem in terms of identifying the equations, boundary conditions, and in terms of discretization, and in terms of putting together a method of solution for coupled equations and converting them into this Ax equal to b type of things and efficient methods. So, in the next module we are going to look at essentially the remaining part, which is how to do the discretization, how to do the grid generation, and especially when we have an irregular geometry, all these problems become even more. So, when you are dealing with irregular geometry, which is often the case imagine you have a car. Car cannot be described in cylindrical coordinates, and any car component cannot be described in terms of Cartesian coordinate system. You will have these step kind of things. Okay. So, when you are dealing with those kind of bodies of irregular shape, and you have to look at fluid flow over those kind of things or through those kind of things, you need to have a more sophisticated methodology, and we are going to look at how to deal with these kind of things. In the first part of the last module, we look at the finite volume method, and we look at how we can generate grids for these odd shaped flow computational domains. And then in the second part, we look at another aspect of reality. We have so far been assuming laminar flow, but turbulent flow is quite common, and for turbulent flow this simplistic approach cannot be used, and we have to do something about it, and that will be done in the second part of the last module.